Welcome to Lecture 12A entitled Changes of Variables in Multiple Integrals, and this is specifically 2D that we're looking at here. The material for this lecture is from section 16.7 of the text and reading assignment 2, reference material objective 3, introduction to lecture 8, Jacobians, and this basically is all contained within the lecture 12 supplement, which is really the only mandatory reading we'd be looking at. Also, I would suggest you maybe review parts of lectures 1A and 1C. So the objectives of this lecture are essentially to show you how to change integration limits and the differential area in 2D for double integrals with the change of variables. And its concepts and visualization skills are twofold. First is the relationship between integration bounds in Cartesian coordinates and the transform coordinates. And secondly, determining the determinant of the Jacobian matrix and the differential area in the transformed coordinates. So these are part and parcel of the same thing. It's just a step that you have to take in order to determine what the differential area looks like in the transformed coordinates. Two notes. One is that in the remaining lecture modules on integration, we use different nomenclature to define transformation matrices compared to what was discussed at the beginning of lecture 8, so as to be consistent with the textbook. And secondly, you may find Lecture 1A, Slide 6, and Lecture 1C, Slide 4 complementary to the discussion in this lecture.
All right, the second slide is as usual, the outline. You can look through this. This is more or less the contents of the material to follow. All right, let's start with a simple one variable problem, which is something that you basically looked at last year. And that is a change of variables for one variable and its relationship to the Jacobian, which we introduced already earlier. So we're going to use a method of substitution and look at the relationship to the magnitude of the determinant of the Jacobian. So the example to be chosen is the one that's shown here. We're going to integrate some function f of x dx between 0 and 1, where f of x is 2 times the square root of 2x plus 1. So using the method of substitution, we basically are going to choose to replace 2x plus 1 by u, which is here. And we'll find it useful to also to get the inverse, which is expressing x in terms of u, which you can easily determine from the expression here. You'll find you get x equals 1/2 u minus 1. All right, under those circumstances, du is 2 dx, or dx equals 1/2 du. So you can go either way. Now, if we're doing a transformation of variables or substitution of variables, there'll be new integration bounds. So for instance, x, which was equal to 0, becomes u equals 1. You do that by just substituting x equals 0 into the expression here. The upper bound will be x equals 1. If you put that in here, then you get u equals 3. And so therefore, the transformed integral will take on this form. This is the original integral, and this is the transformed integral. So this u basically is from this expression here. All right, let's look at this into a little bit more detail. Again, we're just taking the information that we've just presented from previously, and now basically written it out here. And again, here at the transformed integral, which was on the previous slide. All right, so now what we'll do is we're going to let x be g of u, and we define dx by du as a 1-by-1 Jacobian matrix J, which is a scalar. For one variable case, it's a scalar. If we were to take the determinant of the Jacobian matrix, if it's a scalar, it's more or less the same value. In this case, for 1-by-1 matrix, basically the determinant is in fact the value itself. So if we were to take the expression for x, okay, dx du, which would be equal to gu, that will give you 1/2. And we're saying that that is representative of the determinant of the Jacobian matrix. All right, now let's go back and look at our original expression, 2 square root 2x plus 1, and dx I've shown here, which is basically the differential in the original coordinate system, Cartesian. And now what I'm doing is I'm placing this with the transformed system, where this is a function of f, evaluated g of u, and g, the determinant of the Jacobian matrix du. And in fact, if you look at the final result here, you can see that the mappings are fairly straightforward. dx is equal to the determinant of the Jacobian matrix du, where the determinant is equal to 1/2, which is essentially dx du. So this is now showing us the relationship between the substitution of variable technique and the actual fact that what we're doing is we're computing the determinant, the Jacobian matrix for the one variable case. All right, this is the original diagram in terms of Cartesian coordinates. This was the area that we were trying to compute. It's under the curve. In the transform system, we basically have a function that looks like this, is y equals the square root of u. And this is the area that you're now computing. That's between u equals 1 and 3. If you look at this area and this area, they're essentially the same. However, this was an easier way to solve the problem. All right, so now we're going to go into the 2D case, and so a couple things that we need to understand right off the bat. So we're going to be mapping from the S domain into the R domain. This picture here basically shows a region, all right, which is the S region, which is essentially defined in terms of two variables, u and v. And then the region, which is in Cartesian coordinates, region R, defined in terms of variables x and y. Now we can map points from this region to this region or the other way around through transformation. And so that transformation t is defined as x is some function of u of v and y is some function u of v. So you might ask yourself, why is a mapping required? Well, here are the 3 points. For one thing, you map points from the interior region of R, here, to the anterior region of S, here. Secondly, you map points at bound region R to points at bound region S. So you're essentially going from some point here to some point on the boundary. If you go once around the boundary here, you're basically mapping the boundary of S. Thirdly, you're mapping differential areas in region R to differential areas in region S. In Cartesian coordinates, you would have a differential area which is dx dy, which would be an infinitesimally small rectangular object. However, that object will take on a slightly different form in the transform coordinate system. All right, next thing is what transformations are required for integration. Well, you need the transformation t, which is the one that was shown here, which is x in function of u and v and y is a function u of v. You're also going to need the inverse. All right, so both of these basically have to be calculable. In this case, u is a function of x and y and v is a function x and y. So what is the purpose of the transformation t? Well, it's useful for understanding how to map points from the S-plane to the R-plane and to map a differential area in the S-plane to a differential area in the R-plane. And t inverse, what is its purpose? It's useful for understanding how to map points from the R-plane to points in the S-plane. All right, so these are the things that we need to, specifically in terms of boundary points. All right, so let's take an example here. These are integration bounds in polar coordinates. X is a function of u of v, but we're going to use u, replace u by r, and v by theta. This is to be consistent the way what you understand being polar coordinates. So x will take on this form, y will take on this form. All right, so what we're going to do is we're going to basically take a region in the r theta plane, which is the one that's shown here. And it shows here, for instance, that the boundary of this region goes from 0 to 1 for r, and it goes from 0 to pi over 2 for theta. If you look at the bounds on the region, there's this red bound, there's this blue one, there's this green one, and then this orange one here. That basically bound the region. This is region S, and this is region R. So what we want is a mapping that essentially takes us from boundaries for this region to boundaries for the Cartesian coordinate system. So we make use of the transformation equation, and we start by basically mapping out each one of these regions and then seeing how those particular boundaries and determining how those boundaries map in the Cartesian plane. So first let's take A. Now A basically here is just a straight line, and it's 0 less than or equal to r is less than or equal to 1, and theta in this case is 0. If you then substitute the value for theta equal to 0 into the transformation equation, then this becomes r and this one becomes 0. So now basically we want to know how this line translates into a line or curve in the xy domain. So we know that r ranges from 0 to 1, in which case x will basically range from 0 to 1 and y is already 0. So this is basically the mapping of A prime, which is this straight line that you see here, which goes from 0 to 1 for x and y equals 0. So next thing is to look at how does this line transform. All right, so in this case, basically, we have r is fixed at 1, and theta can vary from 0 to pi over 2. So if we substitute for r equals 1, this becomes cos theta, and this becomes sine theta. All right, so next thing is to figure out, all right, how this basically relates to boundary in the xy plane. So in this case, basically, since we have cosine and theta here, the value of theta will range from 0 to pi over 2. And that means cosine theta will vary from 1 to 0, or put it in the compact form, 0 is less than equal to x is less than equal to 1. The next step, though, is to find a function y. So a y is a function of x. And so here we make use of a trigonometric identity. If we were to take x squared plus y squared, we know that's equal to 1. Therefore, we can express y in terms of x. It's just the square root of 1 minus x squared. And it's a positive value. And so that means for x ranging from 0 to 1, this tells you how y ranges. And this is nothing more than a quarter of the circle. It's this region that you see here. So this line transforms to this line here. So the next line is this one. How does this line transform? All right, so in this case, basically, we're going from, again, r is ranging from 1 to 0, whereas this case, theta is held at pi over 2. So if we go back to the transformation equations and substitute in pi over 2, then this term becomes 0, and this basically just becomes r for theta equal to pi over 2. So in this case, x equals 0, and y ranges from 0 less than equal to 1. So that's basically this line that we see here, along the y-axis. The last one is this line, the orange line here, where r is equal to 0, but theta ranges from 0 to pi over 2. All right, so if that's, in that case, if r is set to 0 and theta ranges from 0 to pi over 2, then both x and y are equal to 0. So effectively what's happening is for every point that you consider along this line, you consistently are mapping onto the same location, d prime at the origin. For every point here, you just repeatedly basically touch this origin point. Now you might ask that it's not 1-to-1. Well, 1-to-1 only applies to the region. It does not apply to the boundary. And so it's perfectly acceptable that it's not 1-to-1 at a point on the boundary. So now basically what we have done is we've mapped out the region in the UV plane, that's the bounds of the region, to the bounds in the XY plane. All right, so let's take an example from the book. This is from chapter 16.7, question 9. You're given S, which U ranges from 0 to 1 and V from 0 to 1. It's a unit square in the UV plane. And you want to find the image of S in the XY plane under the following transformation shown here. All right, so we have basically 4 segments to consider, and so we're going to have to do 4 separate calculations. So in this case, U ranges from 0 to 1 and V equals 0. In this case, basically, U is held at 1, but V ranges from 0 to 1. In this case, V equals 1, but U is ranging from 0 to 1. In this case, U equals 0, and V ranges from 0 to 1. And so for each one of these color codes, I basically have shown that here. Here are the conditions with respect to the boundaries in the UV plane. So now how does this transform to boundaries in the XY plane? Well, we have to take each one of these in turn and make use of these transformation equations. So if V equals 0, then X equals U squared and Y equals 0. If U equals 1, and V ranges from 0 to 1, that means that X basically will become equal to 1 minus V squared, and Y will be equal to 2V. You just substitute in U equals 1 here, and this just becomes 2V. In this case, for 0 less than equal to U is less than equal to 1 and V equals 1, make the substitutions into the transformation equation, and you end up with X U squared minus 1 and Y equals 2U. And finally, for the last one, basically, we have U equals 0 and V ranging from 0 to 1. In that case, this becomes a 0, this becomes 0, and you're just left with minus V squared, Y equals 0. All right, so now we can look at the segments in the XY plane. We're given here that X is equal to U squared, but U ranges from 0 to 1, which means X ranges from 0 to 1, and Y equals 0. In this case, X equals 1 minus V squared, and V ranges from 0 to 1, and so that means the the x value will range from 0 to 1 as well. However, now we have to figure out, well, what is y going to be? And so here we basically solve this equation. We're trying to put x in terms of y. And the simplest way to do that is to essentially take this equation and square it, and then divide through by 4 so that you have v squared in terms of y squared. And then you can make a substitution for v squared, and simplifying, you end up with this expression that you see here for y as a function of x. In this case, basically, you have u is defined from 0 to 1. And so in this case, basically, you have minus 1 being the lower bound for x and 0 being the upper bound. Similarly here, we basically have to express y in terms of x, and same idea again. In this case would be to express u in terms of y, and so if you take y divided by 2 and square it, that's equal to u squared. Substitute back, and finally you'll end up with an expression y equals 2 square root 1 plus x. And the last one basically is x equals minus v squared. V is ranging from 0 to 1, and so that will tell you that x ranges from minus 1 to 0, and y equals 0. Now if you plot this, then basically you end up with a shape that looks like this. So you've gone from a square to an object which is definitely not a square. So this is the process you have to go through, in terms of determining what the bounds for the region are in the transform system. All right, so now we want to look at differential area. How do we map a differential area in Cartesian coordinates into a transform system? And essentially what we're looking at is an expression that finally will look like this. This will just going to become the determinant of the Jacobian matrix, du times dv. All right, just some background information. This is not in the textbook, but I think it might be helpful to understand how we get or arrive at this expression. And you're not responsible for this. So differential areas in a plane can be described geometrically as the magnitude of the cross product of two differential basis vectors in a given coordinate system. And clearly we're starting in a Cartesian coordinate system. So for instance, if you have a vector dx, 0, 0, and 0 dy, 0, 0, and you basically take the cross product, right? Then this in a 3D system would be pointing in the z direction, but we're just interested in the magnitude. And so if you take the magnitude, it's dx dy, which is the area, would be the area of a small rectangular object. Okay, note this area is rectangular as I mentioned, but it doesn't depend on position x naught, y naught. So you can take any point in the xy plane, perform this calculation, and you'll find that the shape remains the same, and you always end up with dx dy. However, let's look at a differential area at a position u naught, v naught, which is in the transform system, and see what happens. So we express the differential basis vectors in a Cartesian coordinate systems in terms of differential basis vectors in the transform coordinate system. So we just say let x be equals to some function of uv, y is a function of uv, and we're going to basically assume a right-handed coordinate system because that basically allows us to find results which are positive. We'll talk more about this later in terms of if you make the wrong choice, what the implications are. Anyway, this is a diagram showing you, for instance, at a given location, this is dxx hat and dyyy hat. In the transform system, you're going to have a u hat and you're going to have a v hat, and a ds hat, which is basically the length, which is the combination of the two basis vectors. Now, what we want to know is basically the relationship between u hat, x hat, y hat, and relation between v hat, x hat, and y hat. Okay, so way you do that is to compute the vector dxx hat and dyyy hat in terms of unit basis vectors u hat and v hat. And so this just means you take the partial of this function with respect to u, evaluate it at the point of interest, du, u hat, plus dgv, evaluate at the point of interest in terms of u and v, dv, v hat. Similarly, for y, you basically take the second expression and take the derivative, partial derivative, du, u hat, plus partial derivative v with respect to v, dv, v hat. So this is now basically the original differential vectors in relationship to the new differential vectors. All right, so I basically put them here again, along with the diagram. And now what I'm going to do is take the original expression for computing the differential area in a Cartesian coordinate system, but I'm going to make substitutions for these terms that you see here, all right, in terms of these new basis, this differential that you see here. So this is in terms of a u hat and a v hat, and this is in terms of a u hat and a v hat. So this term basically now becomes this term, and this term that you saw here now becomes this term. So there's a u contribution, a v contribution, a u and a v. And now if we take the cross product of this and take its magnitude, then we should get an interesting result. All right, so that's exactly what I've done here. This is basically this cross product. Now if you do this calculation and take its magnitude, and this is an exercise for you to do, you'll end up with this expression. Now, this is a purely active gymnastics. I could define this or describe it in a slightly different way, that if I were to put things in a matrix form as shown here, u hat, v hat, and z hat, and these in terms of the new basis vectors, dgu, dgv, 0, dhu, dhv, and 0. And then I take this matrix and I take its determinant and then take its magnitude, du, dv. These two would be equivalent to each other. So essentially, it's just another way of describing it. Anyway, if I take this, right, I notice basically if I take its magnitude, it would be more or less the same as if I had just taken a 2 by 2 matrix and just taken the determinant of this expression here. And so this is where this Jacobian matrix determinant comes from. This is just a simplified version, but this is in a form which we totally understand. This is a Jacobian matrix, and it's the determinant that we've computed, which would have been the term that you see up here. So here is basically finally summarized. Now, the shape of the differential area in this case is a parallelogram, but its shape depends on position in general. It'll depend on location u0 and v0, whereas in Cartesian, essentially you ended up with a square or a rectangular object, and it didn't matter where you were in the xy space, you end up basically with the same shape. All right, so let's do an example calculation using polar coordinates. Let u equals r, v equals theta, x equals r cos theta, y equals r sine theta. Compute the determinant of the Jacobian matrix. So first, let's get the partial derivatives of all the combinations, dx dr, dx d theta, dy dr, and dy d theta, and put them in the appropriate elements in the 2 by 2 matrix. So this is basically the Jacobian matrix. If you take these values and plug them in, you end up with this. Now you have to take the determinant, which is this times this minus this times this, and you end up with r. So this is essentially the determinant of the matrix is r. And r, of course, will be a value where it's greater than or equal to 0. So it's always a positive value. All right, so when you compute dA then, we said it was going to be the Jacobian times the new differential elements, which would be dr d theta. So that means dx dy transforms to r dr d theta. Right? Turns out these new basis vectors are orthogonal to each other. So this is an example. This is dr r hat, and this is r d theta theta hat. You can see r d theta shows up here, and dr shows up here. And this is going to be a right-handed coordinate system because theta is taken in a direction which is counterclockwise. If you look at these expressions, this basically will be a right-handed coordinate system. And the differential area, it will be a parallelogram. Here it looks like it's not, it's curved, but in the limit, if you make it smaller and smaller, this just becomes a parallelogram. If you want to look at this, you can. There's a URL link here. All right, now there's another way to do things, which is perhaps a little bit more powerful because you're not restricted to doing a mapping from a 2D to a 2D, but you can actually do a mapping from 3D to a 2D. And this is something we'll be exploring in class 19 and 20 when we discuss trying to compute the surface area, for example, of a curved surface. Anyway, the basic idea here that we want to illustrate is that you start with some object. This is a region S in the UV, and you want to transform that to an object in the XY plane. So what you see here is some point U0, V0. You make a perturbation delta U this way, and delta V in this direction. Here, you're holding U constant. Going along here, you're holding V constant. And then you have the transformation, X in terms of UV, H in terms of UV. So this transforms into this object that you see here. Now, if you look at this, this is a position vector, which is a function of U and V from here. In one case, you're going to hold U constant, and you're basically mapping out a line. And over here, you're mapping out another line, which is when you hold V naught constant. Okay, and so this is a position vector for this line and this line. So this basically defines a region just based on those two lines. You just transform this over here, and you transform this over here. All right, so the next thing would be to sort of define what is the vector that defines going along this line and the vector going along this line. Well, this is nothing more than taking the derivative to form the tangent vector. All right, and so in this case, you can see you're going from U naught to U naught plus delta V naught, U naught, constant U naught, and basically varying V naught. And in this case, you're essentially holding V naught constant and varying U naught. Right, and this is then showing if you compute dr du, which is the tangent vector, as you move in a particular position, holding basically along the U direction, which would be in this direction here. Then you can expand it out in terms of X and Y hat components. It looks like this, based on the transformation equations that were provided. So this would be side A. For side B, it would be along this direction. Right, and so this basically is the starting point, and now we know that the area of this would be, again, the cross product, taking the magnitude of the cross product through vectors to determine what the differential area will look like. All right, so the differential area would be just the magnitude of the cross product between these two line elements, which are shown here. And if we then now go ahead and basically take the information from the previous slide, dru du would have been this term that you see here. There was no z component. And dr dv would have been this term. And this would be the determinant that you're computing, and then you're taking its absolute the magnitude of it. If you do that, you'll end up with the expression that you see here. This is exactly the same expression that we saw using the different approach previous slide. Now, if you want more information about this, you can find it in chapter 15.10 of the book by Stewart, 7E Calculus. We've taken the pictures basically from the textbook. All right, so here we are just summarizing then finally that this becomes this, right? But this can be written in matrix form. If we were to take the determinant of this matrix, which is the Jacobian matrix, you'd end up with the expression here. And so this can be simplified down to something that looks like this. All right, so next thing would be to sort of put everything together in the form of a theorem. This is theorem 16.8, change of variables for double integrals. Again, you're given a transformation that maps a closed bounded region S in the UV plane to a region in the XY plane. And again, we're assuming that T is a one-to-one in the interior of S, and G and H have continuous first partial derivatives. If F is continuous in R, then this is now the generic expression for computing the integral in the region R, and essentially what it would look like after transforming into a different system involving variables U and V. So you would take the value of X, basically express it in terms of function U and V. Value of Y would be in terms of function U and V. So this whole expression is a function U of V. And you have to compute basically the determinant of the Jacobian matrix times the dA, which would be, in this case, would be du dv as shown here. Now, in the book, basically, there's an issue that comes up. The book basically is taking the magnitude of the determinant of the Jacobian matrix. Why is this? Because if you basically set up a coordinate system, a transformation, which is not right-handed, then when you take the determinant Jacobian matrix, you end up with a negative value. If you take a right-hand coordinate system, you'll end up with a positive value. Because the person putting a transformation together may not realize whether or not they have left or right-handed, the simplest way to rectify the problem is just take the absolute value. And this is what the book has done because they did not want to describe some of the details behind the scenes. So keep this in mind. All right, so just remember, it's right-handed coordinate systems, you'll always end up with a positive value. If it's left-handed, it'll be negative, but to avoid that from basically happening, we just take the absolute value. Okay, so this is sort of explanation as to why you get negative. So for example here, if x is this function u and v, y is a function uv, let's basically say we swap these two. We put them in a different order. If you do the determinant of the Jacobian matrix for the first case and the second case, you'll find that the two expressions are not the same. However, they are related to each other by a negative value. So in one case you get a positive value, in the other case you get a negative value. And so which one is correct? Again, this goes back to what we just discussed in the previous slide. It's the distinction between right-handed and left-handed coordinate systems. All right, so you can just read this for yourself. All right, so let's do an example calculation using polar coordinates. Here's basically the integral that you're supposed to calculate. And because we see an x squared and a y squared here, it seems obvious to choose polar coordinate transformation. So let x equals r cos theta and let y equals r sine theta. And so we compute the partial derivatives, and then we compute the determinant of the Jacobian matrix. And so the differential area element dx dy now becomes r dr d theta. What about the integration bounds? Well, we know from the previous slide, right, that when we have basically an integration bound from 0 to 1 minus square root x squared, which would be essentially, this is the upper bound of the integral, this is the lower bound, and from 0 to 1, that's from here to here. This is equivalent to this domain region in the UV plane. And so we know this transformed to r value from 0 to 1 and a theta value from 0 to pi over 2. So we can take this expression now and transform it directly into this expression in terms of dr and d, in terms of r and theta. X squared plus y squared just becomes r squared, so this becomes 1 minus r squared. And determinant of the Jacobian matrix is r. And so we now just have an integral in terms of pure r, and this just becomes an integration that you can perform. So integrate first with respect to r, and having done that, you integrate with respect to theta, and you end up with the result that's shown here. All right, that concludes Lecture 12A. Thank you for listening.